we will talk about momentum. So let's say we have a car. Now we know that if we try to push any of the cars, generally they are difficult to push, and we apply a lot of force, then also the car doesn't move easily. On the other hand, let's say that we have a bicycle. So what happens when we apply a small force to a bicycle? The bicycle is so easily pushed, right? It is easy to push. Now, how do we differentiate between the objects which are difficult to move, the objects which are easy to move? Now, when we apply unbalanced force and we push them, the velocity changes. Like if we apply a force to the bicycle, then the bicycle probably goes at a faster speed or velocity than as compared to the car. The car doesn't even move. That is because the car has a very, very high momentum, right? And bicycle has very low momentum. The object with a higher momentum, which is like difficult to move, the change in the velocity when we apply this unbalanced force will also be very, very small, or in fact negligible in the case of the car. But in the case of the bicycle, if we give a small push or if we apply unbalanced force, then the velocity changes. So what we can say is, it is easy to change the velocity of a bicycle and not of a car. Now, the similar examples, if I give you, let's say we have a rock, a huge rock, and let's say if I have a small stone, what do you think? Whose momentum will be actually more and whose rate of change of velocity will be more? The rate, if we apply a small force onto a small stone, then the velocity of the stone will change very easily, right? The rate of change of velocity will be more in this case. However, for a huge rock, if we apply the force, its velocity will not change. It might just not move only. So the momentum of the rock is very large. These examples, what we have just discussed, they show us that this quantity momentum, the mass of the objects that we are considering, and the velocity, they are related, right? Because we said that a heavy object will not move and its rate of change of velocity will also not be very large, and so the momentum we say is large. So how are these two terms related? With these three terms we can define momentum. The momentum, it is defined as small p of an object is defined as the product of its mass, that is m, and its velocity, that is v. So we say p is equal to m into v. So momentum is mass into velocity. So if let's say you have two different objects, so first of all you have to check whether whose mass is more. Whichever object has a greater mass, then the rate of change of velocity will be lesser in that case if you apply an unbalanced force, and hence the momentum will also be more. So that's how we talk about and we determine the momentum. We have two objects here which is on the screen. One is auto and another one is train. So if we compare these two, first of all, whose mass is more? Obviously the mass of the train is more as compared to the mass of the auto rickshaw. So that's why we say momentum of the auto rickshaw is less than as compared to the momentum of the train. Now, momentum has both direction and magnitude. Because, why do I say that? First of all, it is m into v, that is mass into velocity. So m has got some quantity, and velocity as such is a vector quantity because velocity has speed and direction both. So that's why the product of mass and velocity becomes a vector quantity. The SI unit of momentum is kg meter per second. Now, this study of momentum, inertia, mass actually brings us to our second law of motion, which states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. Now, rate of change of momentum of any object is proportional to the force. That means, let's say if we apply a small force to an object, then there will be small change in the momentum. If we apply large force to that same object, the change in the momentum of that object will be large. So it is proportional. Rate of change of momentum is proportional to the applied unbalanced force. Let's say we have the same cycle. The initial velocity of the cycle is u, mass of the cycle is m. If we apply, let's say here, an unbalanced force, which is capital F, then in time t, let's say the cycle moves to some distance and it now attains a final velocity v. In this case, the initial momentum of the bicycle we say is p1, let's say. So p1 is mass into velocity. So it will be mass of the cycle into the initial velocity, which is u. Final momentum will be p2, which is mass into the final velocity. Now what will be the change in the momentum is p1 into p2 will be the change in the momentum. That is equal to m into v minus m into u. That is mass into final velocity minus mass into the initial velocity of the cycle, which will give you rate of the change of the momentum, which is equal to m into final minus initial velocity divided by t, and that is proportional to the applied force. This k, what is written here, is actually a constant. So F is proportional to k into m into a, because acceleration is v minus u divided by t is acceleration. So we substitute the value of acceleration into this and we get F is equal to k into m into a, where this k is a constant, which is known as the constant of proportionality. And that's why, since it's a constant, we remove it and we write F is equal to m into a. So this is our second law of motion, right? Second law of motion talks about the momentum and the force which is applied, the unbalanced force. The second law of motion is applied to very many situations in our daily life. For example, in the game of the cricket, you must have seen, now this is a player, now he is trying to catch the ball. Now instead of catching the ball here at this instant, he takes his hand down and he takes some time to catch the ball. Now why does he do so? See, again, this is second law of motion. The mass of the ball will remain the same whether he catches the ball at the first instant, that is here, or whether he catches it later time, right? The mass of the ball will remain the same. The velocity is also the same. What is different when he is catching the ball at a later time is that the time is more. So that means it depends on the time also. What happens with the time? As the time is more, the impact of the ball onto his hand will be less because he is gaining the time. That's why he doesn't catch this ball at this first instant, because this ball is going to hit his hand and the impact will be large. Now, you must have seen the jumpers. So when they jump on that cushion. They don't jump on the ground. That is because that cushion, it's a bouncy kind of bed. He is gaining the time again. And that's why the impact on his body will be less. So these are the examples of the second law of motion. Now, after discussing the second law of motion, we move on to the third law of motion. And the third law of motion states that when one object exerts a force on the other object, the second object instantaneously exerts a force back on the first object. And these two forces are always equal in magnitude and opposite in direction. That is, if let's say if I punch somebody, or if I punch, let's say, a wall, my hand is going to be hurt because the more force I am applying onto the wall, the similar force is applied back onto my hand. So if I punch a wall with a lesser force, I'm not going to get hurt. But if I applied a very large force onto the wall, then my hand is going to be hurt. So every action has an equal and opposite reaction. That is what is the third law of motion. These two forces are always equal, but they are in the opposite direction. Here there are few kids who are playing football. Now the force exerted by boy on the ball will be equal to force exerted by the ball on his leg. The harder he is going to hit the ball, he is going to hurt his leg, right? So these two forces, they are known as action and reaction forces. What was action in this? Action is the force exerted by the leg on the ball was the action, and opposite to this, the reaction was the force exerted by the ball on his leg. So that was the reaction. So there are two forces and these two are opposite in direction. Now, the third law of motion is what is applied in most of our works in our daily life. For example, how are we able to walk? How do we walk? We think that, we lift our leg and that's how we are able to walk, but that's not so. We are not just lifting the leg, we are actually pushing the road behind. First, using this leg, we are pushing the road behind. So because there is friction between the road and our leg, due to that, what happens is, because we are pushing the road behind, the road is also pushing us ahead. That's why we are able to move. There are many other examples, like when we jump into the swimming pool, what do? When we jump into the swimming pool and we are standing on that board, first we take a push. So we push the board down. Why do we push the board down? Because the moment we push the board down, the board is going to push the swimmer in the upward direction. So pushing the board down was the action force, because initially the action of the swimmer was to push the board down. But what was the reaction? Reaction was that he comes up with the equal and opposite force. He is pushed upwards. So that is the reaction force. So these two are, as you see, the red and the black arrow are always opposite in direction, but they have equal magnitude. Now, if he, let's say, pushes the board down with a small force, he is not going to get enough jump. But if he pushes the board a little harder, then he is going to be getting that push that he requires. So this is action and this is reaction force. Now, next example is recoil in a gun. So you must have seen that when you fire a gun, what happens? You can see that from some distance also, that the person who's holding the gun, his gun also moves a little back. So why does it happen? That is also because of the third law of motion. When you fire a bullet, so the bullet goes forward. Now there is a force that is applied onto the bullet, and because of this force, the bullet is pushed forward and it accelerates. Now this is an action force, that the bullet moves forward. A force is exerted on the bullet. Now, because a force is exerted on the bullet, in turn, the bullet also exerts force on the gun, which will be in the backward direction, right? So acceleration of the bullet is forward and the bullet also exerts a force on the gun. So this is what is known as the recoil. When the bullet exerts the force on the gun moves back. Now, you may ask me that, why is that the gun doesn't move very fast or the gun doesn't go in the backward direction? That is because as compared to the bullet, the mass of the gun is very, very large. And what did we learn in the second law of motion? That if the mass is more, then it is very difficult to move the object. That means why? Because its momentum is more. So that's why you will see only a small jerk in the backward direction when a bullet is fired, and not that the gun is going in the backward direction. The gun doesn't go in the backward direction because it is heavy. It has a greater mass as compared to a bullet. This is what is known as a recoil in a gun. Now let's say had the bullet been of some greater mass as compared to the small bullet what we just studied. Now the more the mass of the bullet, then the more will be the recoil, because that bullet is now heavy and more amount of force will be exerted back on the gun. So this is again an example of how a third law is applied while we are firing, right? So in this case again, the action was the acceleration of this bullet in the forward direction was the action force, and the reaction was the recoil of the gun. So this was the reaction. So there's always an action and a reaction opposite to each other. Now what is this person trying to do? The person is trying to jump from the board onto the footboard. So what happens when he tried to jump from the board will slightly move backwards, that is in this direction, and this backward motion will only give him that force to move forward, right? So again, there are two kinds of forces. So there are many examples like this which will tell us that there are equal and opposite forces. That is, every action that we do has an equal and opposite reaction to it. If we have two objects, the third law states that every action has an equal and opposite reaction, right? If we have object 1, object 2, then the force that is exerted by the object 2 onto the object 1 will be F21, and the force exerted by the object 1 onto the object 2 will be F12. So I hope you must have understood the three laws of motion, and also the concepts of inertia, mass, and momentum. Now in the next video, we will solve some of the numericals which will make your concepts much more clear with regards to these first, second, and third law of motion. So thank you for watching Edupedia World videos.